Okay. All right, let's talk about exponential growth and decay. We're going to use Newton's law. There's Newton had a law of cooling and heating that we can use here, and logistic growth and decay. And growth, we think, you think about growth, it's increasing. Decay, we're going to start with a lot and go down to a few. So when we think about those, with the formulas for that, you've got a sub 0. That means the initial amount. E to the kt. Whether depending on what k is, that tells us if it's growth or decay. If k is a positive number, it's going to be growth. If k is a negative number, it's going to be decay. That's how we're going to know that. T is going to be time. And unlike finance problems where time was always in years, that time can vary, and it kind of tells you in the problem, depending on what you're dealing with. If you're dealing with fruit flies, it's going to be in days because their lifespan is very short. But if you're dealing with like carbon dating, it may be in years. But they will tell you in each problem what time is it, what dimension that's in. But it doesn't affect as far as your formula goes. They've got two different formulas, but they're exactly the same. One just uses an A, and the other one uses an N. They're exactly the same. There's nothing different about those. It's the PERT formula from finance problems. Your initial investment, E to the RT, where R here is K, and that's our growth rate or decay rate. Based on that. That's the difference. There's just context. It's the same kind of problem though. So this section should end up being not too bad. So let's look at our first example, and we've got N of T. So the amount of some bacteria or something like that. Some sort of cell. That's easily. Doesn't matter what kind it is, but they're telling us that 100 e to the 0.045 t is the function that models the growth or decay. Why is this growth? Positive k value there, that kt there. So we know it's a growth. The initial amount of cells. Can we look at it and tell that? 100. Yeah, it's like the principal investment in the PERT formula. So it should be 100. Technically, it's putting in a 0 for time, and that ends up being 100 times 1, which is 100. And we'll do grams because you can measure. You know how much one cell weighs. You can measure how many you've got in weight, or a mass, not a weight. Okay. What is the growth rate? Growth rate, remember, is the K in front of the T. So it's 0.045, which we can convert over to a decimal, 4.5% growth. 4.5% growth. Okay. If we were to graph that, we would see it's increasing. So you could graph that with your graphing calculator. Absolutely easy. Just type that in and see what it does. It's an increasing graph. Okay, so that can also help us determine if it's growth or decay just by simply graphing it. Not a big deal at all on that. And now, what's the population after 5 days? Okay, so our initial formula is N of T equals 100 e to the 0.045 t. After 5 days, well, it must mean that t is in days here. So we're going to find N of 5. That's all we're doing. So crank that out with a calculator, and we'll go 2 decimal places on this. 100 e to the 0.045 times 5. 125.23 grams. G is the abbreviation for grams. That's the amount, the population, or the size of our population, mass of it there in that problem. Okay. If they ask you for the population after 20 days, what do? Plug 20. Really, really simple stuff there. Okay. Now here's where it gets into why this is in the chapter about solving exponential and logarithmic equations. How long will it take to reach 140 grams of bacteria? Okay, so we're looking for how many days that is. So we're looking for what variable? T. It's the only variable in our problem. So we're saying 100 e to the 0.045t is equal to what? 140. Technically it's 140 grams. So what do we do to solve that? Divide by 100 e to the 0.045t is equal to how much? 1.4. If you are, we can go to decimals here. You know it's gonna, we're gonna take a natural log here at some point. So natural log of both sides, right? To get the variable out of the exponent. Nice here because we're using natural log. The e and the natural log cancel. 0.045t is equal to natural log of 1.4. How do we get t by itself? Divide by 0.045. T is approximately, and we're going to go 2 decimal places here. So we'll take the natural log of 1.4 and then divide that by 0.045, our growth rate. 7 point, round up, that'll be 0.48. A little over a week, we've gained 40 grams of whatever kind of cell we had to begin with. Doesn't necessarily matter what kind it is. Okay. Same situation. How long does it take to triple the population? Okay, so this is like those financial problems. It's exactly the same stuff, and that's what I want you to see here. Oh, it's the same stuff. It's just we're talking about sales instead of money. Okay, so tripling the population. How much would tripling the population be? 300. If we started with our initial amount was 100 grams, tripling it would be 300 grams. So we do the same problem with the 300 over there. Maybe actually a little easier math. Same operations, everything's the same there. Natural log of 3. Divide that by 0.045. How much time does that take? 4 point how much? So we got natural log of 3 divided by, what is it? 0.45. Yeah. Remember the 0. 24.41. Yeah. Not 4. 24. Yeah, 41. Almost 24 and a half days to triple the population. And we're assuming that none of the population dies in that time. Okay, pretty easy, right? Same thing we've been doing, it's just in the context of something else. So let's look at example B, and here's our equation. They're using the n sub 0 and all this, and they're telling us that t is an hour. So say it says if the number of bacteria doubles in 3 hours, find the function for the culture. Okay, so if it doubles in 3 hours, so they don't tell us anything. It seems like they tell us nothing about this situation other than the bacteria doubles in 3 hours. So what's the only thing they did tell us? 3 hours is T, right? But then they said that the population doubles in that time. So if the initial population was 1, when it doubles, it will be 2. So we really do have a lot more information than that. The only thing we don't have is the growth factor. We got to find that. Okay, so 2, 1, e to the k times 3. So we're replacing the population, n of t, with 2 because it doubled. Initial value is 1, e to the k times 3. So we want to work that out. Find out what k is. Find our growth factor out of that. Yeah, divide by 1. T equals e to the k 3k, or 2 equals e to the 3k. Then what? Natural log of each side. So k is natural log of 2 divided by 3. So natural log of 2 divided by 3. 0.231. We'll go 3 decimal places on that because that's what our first example did with the growth rate. 3 decimal places is pretty common for growth rate amounts. Okay. Now, so that's our growth rate. Now, n of t equals n sub 0 e to the 0.0 or 0.231 t. So there's our initial function out of that. That's what it asks us to find the function for the culture. That's our initial function. We needed that growth rate in there. Now, that just means for the culture, that we still don't know how much we had to begin with. Okay? Doesn't matter how much we have to begin with. Once we get that information, we can crank out any amount at any time that we want to. Okay? All right, so let's look at part 2. How long will it take the bacteria to triple? So how do we set that up? Yeah, same thing. Step 2, put 3. But this time we're looking for what? The time, not the growth rate. We know the growth rate is 0.231. We're looking for t. E to the 0.231 t. We know that natural log on that side is going to cancel out the e. And so natural log of 3 divided by 0.231. 4 point, how much? 7560. Yeah, let's go. Hours. Remember, time is in hours. They told us that at the beginning of the problem. And they're going to give you that kind of information, what time is in, because it does vary with this type of problem. Very easy on the growth and decay. Remember, growth is going to be a positive positive K value. Decay is going to be a negative K value. As far as how you work the problem, that's it's not going to change anything there. Okay. All right, let's look at Newton's law of cooling. It has a kind of a formula that goes with that. T is your temperature, your room temperature, and then U sub 0 is your initial object temperature. And then you got e to the KT here. So that's your cooling rate, and then time and hours, minutes, depending on what you're dealing with. Usually, so what this is used for, one of the applications of it is determining time of death. Kind of morbid way of thinking about it. It is used for that the human body cools off at a certain rate, depending on the temperature of the room that body was found in. So if someone comes upon a body, the coroner comes and they take a temperature off that body, and that can help them estimate what time or how long that person's been dead. Because once your heart stops, your body temperature starts going down. Okay? And so that's one application of it. Another application would be if you produce like I did programming at a place in Jackson that makes pill bottles, and they did injection blow molding, which takes plastic and puts it in this mold, and it's like just big water plastic, and then it pushes air into it and heats that plastic up. It's real hot, and the air blows into it and it fills the mold up, and it's the shape of a bottle. They actually made the Tums bottles, is one of the products they made, and then they made the orange prescription bottles that we all get at the pharmacy and things. Made a bunch of different bottle products like that, but they had to have a time in between when that thing came out of the mold before someone could handle it and put it in boxes and sort it and all that sort of stuff. So that how long did it take it to cool off? And what they did is they figured out how long it takes to cool off and the average temperature of their room, the production room, and they had this conveyor belt that's bringing these pill bottles down, and they made it long enough that when they rode down that conveyor belt, they were cooled off enough for someone to handle by the time they got to the end. They didn't just guess, we'll make a 50-foot conveyor. No, they actually said, okay, we want it as short as possible, but it's got to be below a certain temperature by the time it reaches the end there. So that was how they, one of the applications of it. It's not quite as morbid as death, but let's say we had an object that's heated to 100 degrees Celsius, which means what's happening to it if it's water? It's boiling. All right, so that's how you can heat something to 100 degrees Celsius. Just drop it in boiling water and leave it for, you can figure out how long you would need it, because law of cooling works in reverse too. And then it's allowed to cool in a room whose air temperature is 30 degrees Celsius. If the temperature of the object is 80 degrees after 5 minutes, when will the temp be 50 degrees? Okay, so the room that they're setting it in is 30 degrees Celsius. The initial temperature of the object is how much? 100 degrees. That's the initial temperature. Okay, so this is one of those things where, did they tell us the cooling rate of this particular object? No. Every object has a different cooling rate, or depending on what it's made out of. Trevor's can there cools at a different rate than a water bottle does, because it's made of different material. So that K changes depending on what material the object is. Okay, human body different than plastic pill bottle. Makes sense. Okay, so So what we need to do first, before we can approach this problem, is find that K value as best we can. So let's start doing that. All right, so our formula, U of T, capital T is the room temperature. U sub 0 is your initial object temperature. E to the KT. Okay? So let's plug in the stuff we know. We know that in this room that's 30 degrees, so 30 goes in the place of T. That after 5 minutes, the object that was 100 degrees, remember 100 is our initial object temperature, it turned into an object that's 80 degrees. What's the only variable in that problem? K. That's what should happen. When you plug all the stuff in that you know, there should only be one variable left. We can't work with it if there's more than one variable. We don't have another equation to build that we could do a system with this, and who would want to do a system with exponential stuff involved anyway? All right, so let's solve that for K. So how do we solve that equation for K? Well, the parentheses are attached to an e to the 5K. So subtracting 30 would just get rid of that 30 first. There's 50 is equal to 100. Well, what's 100 minus 30? 70. So 70 e to the 5K. And then it turns into a pretty easy problem. That looks much less complicated than that original thing did, right? Divide by 70. 5/7. You can get that as a decimal if you want to. I just didn't want to pull up the calculator till the end here. And I'm going to leave that as a fraction anyway because I don't want to round it until the very end. Remember, guys, you don't round until the final answer. Absolutely. Natural log of both sides to get rid of the e. Natural log of 5/7 is equal to 5K. Divide by 5. We want K out of that. Natural log 5/7 should get a negative. What's our temperature doing? It's going down. It's decreasing. So this is like an exponential decay in temperature instead of population in this case. Okay, and then divide that by 5. Negative 0.063. Okay. 3 decimal places there. Or not 6.3, but 6.73. Yeah, I lost the 7 and it says 7.3. There you go. 3. Technically, that would be called in science class 3 significant digits. That's what my chemistry teacher in college would say. You're going to go to 3 significant digits. That's what he every time we did anything. I was like, oh, okay. I still don't understand that. Actually, I do now, but I didn't then. Now, that gets us the K value. We still haven't answered the question that they asked. The question that was asked was, when will the temperature be 50 degrees? We still haven't answered that. All we've done is found the K value out of that, which is great. That's what we need. So we need to know. So we're taking U of T, the final temperature. Now we have this e to the negative 0.0673 t. We've got that function going. Well, we know the initial temperature of the room is 30. We know the initial temperature of the object was what? 100. So we know a lot of this stuff now. So we're going to take that function and set it up so that we want to know how long does it take the temperature to get to 50 degrees. Set it equal to 50, absolutely. Yeah, then do the same steps. The only difference is we're finding what variable this time? Time. Let's subtract 30, 20, 70, divide by 70. 2/7 e to the negative 0.673 t. Natural log of both sides. At some point, this should get boring because you're doing the same steps over and over and over. We were doing financial problems, we were doing the same thing as we're doing with the exponential growth and decay stuff, Newton's law of cooling, same stuff over and over. So when we divide, so let's go one decimal place on minutes because our time is in minutes here because the original problem told us something about 5 minutes. So that's what tells us what time is. So 18.6 minutes. Anything beyond that, as far as with minutes, you're getting into half second, milliseconds and type of stuff. And I don't know that we're that accurate that we can say, oh, well, it's 18 minutes, 0.6 would be 37.56 seconds. I don't think we're that accurate that we can say that. Okay, so that's why I'm going one decimal place there. But the math's not that hard. Getting to the problem that you've got to actually work is where the difficult part comes in. Okay, but with the cooling part, you got to remember, and with the growth and decay, how many variables should you have in a problem that you have to solve? One. That you've got to make sure that you've only got one variable. If you do that, most of the time you're going to end up okay. You're not going to miraculously make up things. All right, so let's talk about the logistic model. And this looks complicated, but it's really not, because you look at the bottom part here. C, A, and B are all numbers. Okay, the C up top is what's called the carrying capacity, and that's what can be sustained by a system. So, like maybe it's an ecosystem or something like that, or maybe it's one petri dish. That would be a miniature ecosystem for bacteria or something like that. So, logistic model. The C, the number that's on top, is your carrying capacity. Sciencey type things there. A is some sort of number. B is a number. It's like your growth rate. It just happens to be in the denominator here with this stuff. Okay. All right. So let's look at a logistic model real quickly. And we want to answer some questions about it. Okay. So here is our function. What's the carrying capacity? 230. Just look at it. What's the growth rate? Negative 0.37. And actually, is the negative already, look at your up here, the negative's already in there. So actually, it's just 0.37. Or how could you express that as a percent? 37%. Sometimes they're going to ask you for a growth rate, and you go to check it. They're going to express it as a percent growth rate or decay rate. Okay. Now, part 2 says determine the initial population. When is the initial population happening? What time? think about the Newton's law of cooling stuff. What was the time when the temperature was 100 degrees? How long had it been out of the water when the temperature was 100? 0. Initial, when you're talking about modeling real life things here, it's right when it first starts. And when it first starts is at 0 minutes, seconds, hours, whatever it is, days, years. And when you're talking about in the finance problems, your account is worth at the day 0 is your initial investment. That's your principal investment. So with initial population, all you're really finding is P of 0. 230 on top, 1 plus 56.5 e to the negative 37 times 0. So what happens to this part? Becomes a 1. Anything to the 0 power is a 1. So we really end up with 230 over 57.5. Well, 1 plus 56.5, which is how much? How much? 4. And I've got on my notes that I did the last time I did this lesson, fruit flies. This is some sort of fruit fly problem. Did anybody take Van Hoose's? Yes. Did y'all do fruit flies? Yeah. We did fruit flies, and when y'all may not believe Miss Walker's old enough to have taught me in high school, but she was twice. So we did fruit flies in her classroom until somebody released them all, and then they were all over the school for a few days. Then they die. They die pretty quickly. But all right, how many flies after 5 days? So if P of 0 finds initial, P of 5 finds 5 days. So we just need to crank that out. I'm going to use a little calculator help. So 230 divided by parentheses 1 plus 56.5. Oops, not yet. E to the negative 0.37 times 5. Close those parentheses. 23.27. Can you have 0.27 flies? No. So hold on. All right, so I plugged all of that in. Make sure if you're typing this all in the calculator, you put the bottom part in, all of it in parentheses. If you don't, it's going to cause a problem. The 23 flies after 5 days, increasing our population. Again, we're assuming none of them are going to die from whatever elements might cause that. And here's where it gets a little tougher, part 4. When will there be 180 flies? That's true. Lots of times we get confused here because the variable's in the denominator and it's in an exponent. But if we think about this as a proportion, yeah, so we can cross multiply then, right? It's 230 on this side. Now, I'm not going to multiply out 180 times that 1 plus 56 and a half e to the negative 37t. I'm not multiplying that out because there's no need in it. Because once I get that here, what really happens is 180 and the 1 plus 56 and a half e to the negative 0.37t, they just swap places because now I can just divide by 180 to cancel that out. (23/18). I'm gonna leave that as a fraction because I know at some point here I'm gonna have to probably take a natural log or something like that. Subtract 1. Over 18. And then I would divide by the 56 and a half. And then I'm going to do a little over 18 divided by 56.5. Math here. So I get this fraction. 5/1017. And I'm using a fraction there instead of the decimal because I don't want to lose anything. I don't want to round until the very end. Take the natural log of both sides. Divide by the negative 0.37. (14.37 days, yeah. Well, several steps there, none of which are excruciating as far as level of what you got to do. But altogether, maybe it looks a little daunting. Key is just making sure you're plugging stuff into the right spot in those models that you're given there. Now, what does carrying capacity mean? If we're dealing with the context of fruit flies, the environment we have can only support 230 fruit flies. That's all we can support in this particular area. Carrying capacity, when you talk about hunting and fishing, the certain area can only support a certain number of deer. So when you think about the carrying capacity of one of the ranches like Big Buck Resort, I think about that place because they have a population control type situation they do there. My father-in-law has, his brother has a farm and they do kind of population control work with TWRA in carrying capacity for the farm he owns in Hardeman County that they hunt on. So carrying capacity just means how many of a certain organism can this environment support. If it gets over that, then things start going crazy and things happen. All right, so the problems you want to look at, page 483, 1 through 29, just the odd ones to get you going with that. Formulas, I'll give them to you, just like I did with the finance stuff on quiz. Quiz tomorrow, test Friday, right? Today's Wednesday. So quiz tomorrow, test Friday over chapter 6. So, a lot of stuff there, but